Hi, welcome back. On today's lecture series, we are going to discuss about per unit reactance diagram. So, in the previous class, we have discussed about the per unit impedance diagram. So, these are the procedure to construct an per unit impedance diagram. So, at initially, we have to choose the base value of the base kV as well as the base MVA. So after that, we have to convert the impedance conversion. That is like to transform the actual impedance to the per unit value. That is in terms of percentage into per unit value. So from this conversion, we have to draw the single line diagram, and the single line diagram can be simplified into the representation of power system components. So that we can able to eliminate the different voltage level across the transformers. So now in the per unit reactance diagram. So may I know what is a reactance diagram? So actually it is a simplified representation of power system. Here it shows only the reactive power component. So here we are mainly focusing on only the inductive load and the inductive and capacitive elements. So here the resistive elements it can be negligible. So okay, it can be mainly used for the determination of fault and fault analysis and for the stability analyzing purposes. So why we have to use only the reactance and why we are not going along with the impedance? That is the combination of resistance and reactance. Because in a power system, the reactance is always greater than the resistance. So the resistance is very low value. So it can be negligible. So because the reactance is always dominating the resistance. So it simplifies the short circuit calculations. Also, it improve the computational efficiency. So that is the main objective of the per unit reactance diagram over per unit impedance diagram. So while doing the empathy, so many of them asking, so why we have to neglect the resistance from the analysis? And they are having too much of a confusions between the impedance and reactance. So here the per unit conversion across a different voltage level. Why we have to do at the different level of power systems. So these are the few confusions which are occurred, which are having among the community, and it has some practical difficulty like by selecting the proper base value and the handling of transformer reactance and the handling of different voltage level in the transformer and for drawing logical etc. So what is the main application gaps? So when we have to use the reactance diagram and where we have to use the reactance diagram and when we have to use the impedance and where we have to use the impedance diagram. So these are the real world system complexity. So here the main software which can be used for the determination of power system analysis. So here in the defined stage, so we have to represent the multi-voltage power system in a simplified format. So for the fault analysis and stability analysis. So here the all the different voltage level can be normalized across the base according to the base value, and mainly we have to focusing on the reactive element compared to the resistive element. So it gives a quick calculation of fault analysis, and we can able to maintain the accuracy for high voltage system. So here the 90% of accuracy can be estimated here for the reactance diagram. So in the ideate stage, so how we have to draw the reactance diagram? So the step number one, we have to select the base value. So here the base value it may be given, or we have to choose the base value. So of the new base MVA and the new base KV for each voltage level. Okay, so here the MVA base is common for the entire system, and the new base KV it changes according to the voltage level. So after selecting the base quantity, and in the step 2 we have to calculate the base impedance. So this is a formula to calculate the base impedance, which is equal to the base kV whole square divided by base MVA, or it may be called as V base whole square divided by S base. S is nothing but an apparent power. Okay, so on step 3 we have to convert the component reactants like the generator, transformer, transmission line, and loads. So with the help of the equivalent circuit of the power system component, so we have to convert the power system component into the reactance component. So it should not contain any resistive value. Okay, so for the calculation of a new per unit reactance, which is equal to the actual reactance divided by base reactance for generator, transformer, and transmission line, etc. So after calculating the per unit new per unit reactance for the various component, so we have to draw the single line diagram with respect to the per unit value. So now we have to verify the circuit, and we have to validate whether the conversion is perfectly done. So here, these are the component wise conversion from the percentage into the per unit value. For the generator reactance, so here we have to determine the per unit reactance of generator. Okay, so here it is used for momentary fault current and the initial fault period for first few cycles only. So it is mainly at steady state conditions only. And for transformer reactance, so it is normally in the range of between 5 to 15 percentage. That is nothing but in leakage reactance, in either in the primary or secondary side, or with respect to primary or with respect to secondary. So here we have to convert the transformer rating and voltage rating. So in the for transmission line reactance, so for the calculation of a line parameter, so the inductor reactance XL is equal to 2 pi FL. It can be calculated per kilometer. So here the series reactance, it dominates in the long line compared to the resistance. And for motor load, it is represented as reactive power during the fault analysis, and we have to contribute to fault current momentarily. So these are the steps for calculation of reactance in the generator, transformer, transmission line, motor, etc. So this is a sample prototype. So these are the data given for a generator, 50 MVA, 11 kV, and the inductor and the reactance will be 20%. That is 0.2 per unit. And for transformer, 50 MVA and 11 to 66 kV, that is primary and secondary, and the reactance of 10%. That is something like 0.1 per unit. And a line. So line the transmission line is the 66 kV for it can be transmitted for over a distance of 50 kilometer, and the reactance is 0.4 ohm per kilometer. Okay. So here they are given the reactance value. They are not giving the resistance value or impedance value. So here we have to choose the base value as 500 MVA, and the base voltage is 11 kV. So here, with the help of the formula, we have to calculate the per unit reactance in the generator, transformer, and transmission line, etc. So all the per unit value, it should be below 1 per unit only. So this is the testing stage. So we have to check the base value consistently, and we have to validate the conversion from the percentage into per unit value, and we have to verify the topology, and we have to test it with the fault calculation of either symmetrical or unsymmetrical faults. So these are the real-time applications. It can be used for fault analysis and for the relay coordination, stability analysis, and industrial power systems. So this is mind map for per unit reactance diagram. So it can be classified into three categories for fundamental, component, and applications. So in the fundamental, so we have to know what is per unit system, and we have to choose the base quantity, and we have to normalize the concept with respect to base quantity, and the excess reactance is always greater than the resistance, so we have to choose only the reactance value. So these are the basic fundamental. And for the component, so we have to calculate the generator reactance, transformer leakage reactance, line reactance, and motor contributions. And according to the application, it can be used for short circuit analysis, relay coordination, stability studies, and the power system planning. So this is an accurate challenge. So why do we neglect resistance in high voltage transmission system, but must consider it in low voltage distribution system? So if you know the answer, you can put in the comment section. And this is another assessment. So here the transmission line of 80 kilometer length, it operates at 132 kV and has a reactance of 0.5 ohm per kilometer. This for transmission line. Now you can calculate the per unit reactance on a 100 base MVA. Okay. So you can comment the answer in the comment section, and from this we can able to know the simplification tool, the normalizing power with respect to base kVA or MVA, and the practical relevance with respect to the designing of production, stability studies, and system planning. Okay, so these are the few references for this topic. Thank you.